Hello everyone, welcome to this NPTEL course of Computational Gas Dynamics. I am Professor Rajesh Ranjan from Indian Institute of Technology Kanpur, and from now onward I will be talking about the computational aspect of this course. Till this time for the first 4 weeks we discussed about the theoretical aspects of this course which was taught by Professor Niranjan Sahu from IIT Guwahati. And now I will take you through how to solve basically these equations computationally, so that whatever you have learnt theoretically can be basically shown on computer. And not only that, we can basically use these approaches to solve much more complicated problems which cannot be handled using pure theoretical approaches. So, let us start. So, this is what you have basically studied so far. We have gone through the review of thermodynamics and fluid mechanics. So, you know the first and second law of thermodynamics, also the equations of motion in fluid mechanics, the Navier-Stokes equations, Euler equations, okay, different conservation laws. You also went through the computational flow basics, okay, isentropic relations, study 1D and quasi 1D flow equations, isentropic flow equations, etc. Area Mach number relation. Then I think we discussed about the normal and the oblique shock waves also, okay, and then finally the quasi 1D flow and the nozzle dynamics, and Professor Sahu also help you solve some of the numerical problems. Okay. So, with the strong foundation in gas dynamics, now let us look at how do we basically make use of the computer that we have. So, as you know that the computers have become very powerful now. We have now GPUs which are enormously more powerful than the CPUs. So, we can utilize these computing resources to solve the equations that we have learnt in the previous lectures. We will also go through the equations in the first few lectures, so that you have a good command on what we are going to solve. The other reason for going through the equations again is that there are many different forms of equations. There are conservative form, there are non-conservative form. Okay, then you may have some or other effect missing. You may have the inviscid equation, you may have the Navier-Stokes equations. Okay, and then some or other limit you may have different ways of solving the same equations, right. So, this area of solving the fluid flows using computations is called the computational fluid dynamics. And this particular course is computational gas dynamics, is because we will be mostly focusing on gases. So, the fluids consist of both liquids and gases, and you have learnt about what is the basic difference between the liquids and gases. The main thing that we want to talk about here is that although the same equations govern both the liquids and gases, in the case of gases you may have high compressibility, right, and because of high compressibility you might have shocks and some other effects which you will not find in liquids. Okay. So, that is why the title of the course is computational gas dynamics, and because of many flows which are around us are basically comprised of gases. It may be the air, it may be oxygen, it may be nitrogen, or maybe rarefied gases also, right. So, there are special methods or algorithms developed for solving the gas dynamics problems. Okay. So, we will be going through this in the next 8 lectures or next 8 weeks. Okay. So, this is what we will be going through broadly. So, in the fifth week, which is the current week, we will go through the hyperbolic systems and conservation laws once again. Okay. And then we will have the basic discretization method. We will look at some simple model equations like let us say convection equation, diffusion equation. We will apply some discretization, maybe the forward differentiating, backward differentiating, central differentiating, and look at the properties of these discretization methods, the accuracy, the stability, and so on and so forth. Okay. And then we will go for the numerical methods for conservation law. We will go through more complicated equations which are maybe non-linear, okay, which can produce shocks, and we will look at what kind of methods we can use for those equations. And then we will go to the Riemann solver, especially for very strong non-linear problems which comprise of shocks. Okay. So, that will be the part of 8th week, and in the 9th week we will go for the shock capturing and TVD methods, total variation diminishing approaches. These are again basically specialized approaches for capturing shocks effectively. As we learn, we will know that because the shocks are infinitesimally thin, it is not very easy to capture shocks numerically unless you have some special methods. So, for example, if you try to use central differencing method, you will not be able to capture shocks. So, it requires certain level of dissipation, but just enough that it should capture the shocks effectively. It should not be diffusing it too much, it should not be smearing it out too much, but at the same time it should be able to capture the shock with the right strength and the right location. So, for that we will go to this shock capturing and the TVD methods, and then we will go to the finite volume approach. Okay. So, as you know, there are three main approaches. One is the finite volume, the other is finite difference, and third is finite element, right. So, finite volume has got certain advantages, okay, over let us say finite difference. Main thing is the basically it preserves conservation in a discrete sense. So, we will look to basically briefly in 1 week how we can use the finite volume to solve some canonical problems. Okay. And then the boundary conditions are very important, especially in compressible flow, because as we will see there are certain waves and they propagate in a certain direction. So, unless we respect those approaches, we will not be able to capture the flow field effectively. So, we will go through that boundary treatment and the solver development, and finally, we will have some applications. We will solve basically I mean moderately complex problem using this approach, and we will also look at some advanced topics. So, that is what will be for the next 8 weeks. Okay. So, let us start with the conservation laws. Okay. So, the governing equations that we have, and as we know already that we have basically the mass conservation, which is the most important one, and then we have the momentum conservation, okay, and then have the energy conservation. Okay. And I am sure you have gone through this. So, the momentum conservation is nothing but basically it is Newton's second law of motion, and energy conservation is basically coming from the first law of thermodynamics. Okay. So, we have gone through this, we will go through them again, and we will see many different forms of writing the same equation. Okay. And if let us say if you are we are talking about flows which happens in gases, you might have combustion. Okay. You might have gases which is going through a scramjet, and at high temperature you might have dissociation, you might have different species formation. So, in those cases you have to add some more species conservation equations also. So, they are specialized topic, basically the reacting flows, okay, or you may have multi-phases. So, we will not be going into those topics, those are specialized topics, and you may refer to appropriate textbooks or lectures for those kind of problems. Okay. So, before we go to the full Navier-Stokes equations, which includes the effect of viscosity, we will look at the inviscid equations. Okay. That means, we are ignoring the effects of viscosity as of now, right. So, when the equations are inviscid, or it is also called the Euler equations, okay, what are the forces which are dominating when we talk about the momentum equation, or what are the terms and energy equation, we will go through them. For the mass conservation, if you look at it does not matter, because the viscosity is not affecting the mass conservation law, okay, whether it is Euler or the Navier-Stokes, the mass conservation remains the same, and you might have gone through the Reynolds transport theorem, or basically if you take a finite volume or a finite element, you can basically derive these equations. You may have basically let us say some mass coming in and some mass going out, and you consider a small element, and then you basically write the laws of what mass going on, mass going out, and when you equate that, you can get this mass conservation, which is can be written for a 3-dimensional flow is as d rho by dt plus dou u by dx plus dou rho v by del y plus dou rho w by dou z, right. So, these are the equations for the mass conservation, okay, for 3D. So, if it is 2D, you will have just basically d rho by dt and plus d rho by dux. If it is 2D, then you might have two directions u and v, and for 3D it is a general equation, right. So, when you are trying to write a code for this, or when you are trying to handle very complicated equations, it is a good idea to write in a very compact form. Okay. So, the one of the compact forms is basically the approach which is called the Einstein summation convention. So, what we are going to do? We are going to give indices. This is also called the index notation. Okay. So, let us say I am replacing, or I am indicating u as u v w as, so you have u, v and w, and we will indicate this is, let us say this is u1 and this is u2 and this is u3, correct. And then you can basically write all of them together as basically ui, right. So, I can be I equal maybe 1 or maybe 2 or maybe 3, right. So, if it is 1D you will have just u1, if it is 2D u1 and u2, and if it is 3D then it is u1 u2 u3. So, then if you write this expression, so you will have basically you can write this d rho by dt plus sigma I equal to 1 to 3 d rho ui, rho is a scalar and u is a vector. So, there will be ui by dxi is equal to 0, right. Let me just erase this part. Okay. So, d rho I equal to 0. So, it is the same thing written in a compact form. Now, what Einstein convention does is that it says that you do not even need this sigma I equal to 1 to 3, right. So, it is understood. So, whenever you have repeated indices, so you have I on top and I on bottom, okay, these are repeated indices. So, it will automatically assume summation, right. So, you can get rid of this part also, okay, and you can write just d rho by dt plus del rho ui by del xi is equal to 0 as the rho ui by del xi equal to 0. This is the very compact convention, okay, and this is very useful in basically let us say you want to differentiate it or you want to basically do some operations. So, this is a very compact way of doing the things, okay. So, this is the same thing is written here, okay. This is also called the index notation, okay, because this I, j, k are the basic indices and x1, x2, x3 are basically x, y and g, right. Now, what you can do, you can open this up, right. So, you can use the chain rule. So, you have basically d rho u I by dxi is equal to, so you can take this one out. So, u I del rho by del xi plus rho del u I by del xi, right, and you can write it this together. Now, you can collect these two terms. So, this is the same and then we have used the chain rule for this and you can collect these two terms, right, and this is nothing but the total derivative of the density or the material derivative or the substantial derivative. Okay, there are many different names for this and this is a very important concept in fluid dynamics. So, if you are talking about the Eulerian versus Lagrangian one, okay, so here basically what we are talking about is that the density following a the change in density following a fluid particle, right. So, you have basically d rho by dt, this is one part, and plus ui d rho by dxi, okay. So, this is nothing but equal to d rho by dt, this is the total derivative of density, right. And if you want to basically write in a long form, so if it is 1D it is like that, if you have 2D then v d rho by dv and so on and so forth, okay. So, there are many ways to write it. If you want to write in vector form, okay, so you can write it d rho by dt plus u dot del rho, right. So, it comes from the expression that you can, the rho depends on both x and t, right. So, this is basically if you are writing any change in derivative with respect to time, so it will be just pure time and then you have d rho by dx and dx by dt, right. So, which is what is u here, right. So, we can basically write the total derivative in this way, right, and you can take this thing together and you can write it d rho by dt plus rho du by dx equal to 0. So, this is another, this is the same thing written in a different way, right. So, now what you can do, you can if let us say if you are dealing with incompressible flow, right. So, this term will go to 0. If the flow is incompressible, that means the density following a fluid particle is going to 0. The total change in density with respect to time is going to 0. That means, this will go to 0 and density cannot go to 0. So, you will left with this expression which is del u I by del x I equal to 0, right. This is basically the incompressible equation, incompressible continuity equation. So, what you will note here is that here we had the time derivative and change in density with respect to time. Now, since the density is constant, the time derivative goes away. Now, what we had a dynamical equation now becomes a constraint on the velocity, there is no density here, right. So, you might have seen the other form which is basically del dot u is equal to 0, right. So, this is the divergence free condition in the incompressible flow. In the compressible flow you have to use either this or this, okay. So, let us go forward and many of you might not be familiar with this notation. So, I have just written this in the vector form also, right. So, this is del rho by dt plus del dot rho equal to 0. This also if you when you expand, it goes to the same form that we had here, and if you take an equivalence of this, the d rho by dt, and this is rho del dot u. Okay, either you can write like that, or basically you can, I mean, for this term you have u dot del rho, and this is rho del dot u. So, this is the divergence term. Again you say that d rho by dt goes to 0, and finally you have del dot u basically going to 0, right. So, this is what is the for the incompressible flow. So, this is the mass conservation, which is same whether it is inviscid or viscous flow. Now, let us go to the momentum conservation, okay, and we will first discuss about all the inviscid relation, and then we will go to the viscous one, because they are slightly more complicated, right. So, as I was telling that momentum equations are nothing but the application of second Newton's law, okay, and what is the second Newton's second law is basically mass into acceleration is equal to summation of forces, and this is what you see here. So, because we are talking about fluid, so we talk about mass per unit volume, everything is per unit volume. So, that is represented by density here, and acceleration basically the total acceleration du by dt. So, the change in velocity with respect to time following a fluid particle, and this is basically the summation of forces. You can have some external force, it may be the gravity, or it may be any other, maybe the magnetic force, if you have such things like that, and of course, the pressure force, which is basically acting on the fluid, right. So, this is in brief way, this is the momentum equation, and you can further basically take this total derivative d by dt and write in this form, okay, u del by del x plus v del by del y and w del by del z, okay, and then you once you put this thing there, you will have this entire expression, okay. So, you can write in this form also, okay. So, you can see here there is one u which is, and there is another u here, okay, the u dot del which is basically giving this term, and then that is multiplying to another u. So, basically this is the convective term, this is the convective acceleration term, okay, because of the change in the velocity, okay. So, this is the unsteady term, okay, this is the convective term, convective acceleration term, and then you have the pressure gradient term, okay, which drives the flow, and then you might have external forces, okay. And the same thing as we discussed earlier can be written in the Einstein notation or the index notation. So, now this vector u is becomes ui, and thus u dot del becomes u del by uj del by del xj. Again you can see this is the repeated index, that means whenever this uj comes. So, if you write it in a big form, so this is, let us say take j equal to 1. So, this will be u1 del u1 by del x1, okay. Fix I equal to, let us say 1, we are talking about the x momentum, I equal to 1 is basically x momentum. So, this I index here represents the direction of the flow, okay, and this j is basically the summation, this is the repeated index, right. So, this will become for j equal to 1 this, j equal to 2 will be u2 del u 1 by del x2. Remember, this will still be 1 because you are talking about I equal to 1, okay, flow in x direction, and this is u3 del u1 by del x3, or if you write in your vector notation u del u by del x plus v del u by del y plus w del u by del z, right. So, how the u is getting convected due to the change in u, v and w, right, and this is the pressure gradient term, okay, and this is the force term, okay. This is the Einstein notation, and if you expand it and let us say I am writing it for 3D. So, this is how your equations will look like, okay. So, again this is the term which is the time dependent term, okay. Then these are the convective terms, this is the pressure gradient, this is the force, okay. Now, this what you are seeing here, that although the flow is compressible, okay, you are basically treating this compressibility term or the density term, okay, separately here on the right hand side, okay. So, what this is called the non-conservative form, okay, and which is not very good if you want to write a code for gases, okay, the flow in gases, okay, and I will come to that why it is not a very good form and what will be the better form. So, let us go there. So, this is the non-conservative form. So, my rho is appearing here, okay, and this entire thing is basically this is the nonlinear term that we talked about, this is the time derivative term. How to convert it to conservative? So, when I say I want to make it conservative, that means I want it to be in the form of rho ui. Okay, the rho can be basically absorbed in the new quantity which we call the conserved variable. So, it can be rho u, rho v and rho w, and there are certain advantages of basically capturing them together, and we will basically see them shortly. Okay. So, to do that, what we will do? So, we will I am doing it in a reverse way, or you can probably start from here. Okay. So, you have this term on the left hand side, right. So, I want to write it on this form. So, what we will do? We will multiply with rho here, okay, and then I will talk this, add this continuity term. Okay. This is nothing but 0. Multiply with u and add this term which is the continuity equation, okay, and then I will basically collect the terms together. Okay. So, this is basically rho, this will become rho du by dt, okay, and then you have basically this rho uj, it comes here, and then ui del rho by dt, okay, and this term comes here, right, and when you collect these two, okay, you get this term, right, because dou rho u by I by dt. So, this is basically rho du I by dt plus ui del rho by dt, okay, and then if you collect these two terms and you take basically ui separately and rho uj separately, right, then you will have these two terms, correct. So, what I am trying to say is that this entire thing that you have, okay, so bring rho on the left hand side. So, you will have rho du I by dt plus uj del u I by del xj, okay, is equal to minus del p by del xi plus rho fi. Okay. After some time, I will basically ignore the forces. Okay. The reason for that, I want to make it simple for the derivation. Okay. As of now, you keep it, and now this term can be replaced by this term. Okay. So, this term can, because both are the same thing. So, we will have basically dou rho u I by del t plus del by del xj rho u I uj, right, that will be the left hand side, and right hand side remains the same, right. So, this form is called the conservative form. Okay. So, this is basically the conservative form that we discussed. So, what changes we see here? We see that the rho is now absorbed in the velocity. Okay. Instead of talking about the primitive variable which are basically rho u, v, w, we are talking about rho u, rho v and rho w, right. But why do we want to do that, right? That is the question, because in incompressible flow we do not do that. Anyway, we do not need it because rho is constant there. So, what happens? Let us look at this, this is the conservative form, and let us say that you want to solve an equation. Let us think of, okay, you have this dou rho u by dou x equal to 0 or some boundary condition. Okay, you want to solve this problem. Okay, and if you have any exposure to any basically discretization approach, maybe in finite difference, okay, so you can have basically you divide this. So, let us say you want to solve this problem between 0 to 1. So, this is 0 and this is 1. Okay, you will have boundary conditions here and here. Okay, this is 1D flow, and then you have d rho by u by dx, and this is let us say my I, this is I plus 1, I plus 2. So, you discretize it into n number of points. Okay, it can be 100 number of points, and this is I minus 1, I minus 2 and so on and so forth. And if you want to approximate the derivative here at this point at I, right. So, what you will do, you can, if you can use the backward difference, which will be rho u I minus rho u I minus 1. So, at this point the value at this point and minus value at this point by delta x. Okay, this is coming from the Taylor series expansion, okay, which you have gone through many times, okay, during your basically undergrad courses and all, okay, in math. Okay. So, this is how you can write it. Okay. Now, let us look at the non-conservative form. I want to solve the same problem, okay, basically del rho u by del x, but instead of doing it in a conservative form, I am doing it rho del u by del x plus u del rho by del x, right. So, once you do that, you have two problems actually. One is that the rho, you let us say you want to do for the same I, and this is I plus 1 and this is I minus 1, and using the same backward differencing I minus 1 to approximate. So, this can be approximated, let us say u I minus 1 by this, this can be approximated by rho I minus 1 by delta x, right. Now, the question comes for the rho and u, what value should use, whether it should be I or should be I minus 1 or should be the average between I and I minus 1, right. So, that so you can, if you can use rho I and u I, then you are making one approximation. If you are using the value at the previous point, you are making another approximation, or you may have an average of these things, or you have multiple choices, right. So, it is not as clean or as basically intuitive as you have in the conservative form, right. The other problem, I said two problems. So, the other problem is that let us say you are doing it from point, let us say 1 to n, right, sorry 0 to n. Okay. So, this is 1, this is 2 and this is 3, and you are adding all the points, right. So, once you are at this point, okay, so because this is boundary condition and this is boundary condition. So, you 1 minus 0 by delta x, then 2 minus 1 by delta x, and let us assume that grid is uniform, that means delta x is constant, 3 minus 2 by delta x and so on and so forth. If you add all of them, then what will happen, this rho u 1 will get cancelled out with this one, rho u 2 gets cancelled out with this one, and similarly rho u 3 will cancel out with something else, and then finally you will have this one also gets cancelled out, and ultimately you will have effect of what is the value at n and what is the value at 0, which is rho u n minus rho u 0 by delta x, right, which is what you expect if the flow is if you are really respecting the conservation laws. So, if you integrate it n to n or basically sum it n to n, you will have only the boundary effects, okay, which is what is happening in this case when you are using the conservative form. If you use the non-conservative form, you can go back and check. So, first case will be rho 1 and then u 2 minus u 1 minus u 0 by delta x. So, let me write it here, u 1 minus u 0 by delta x and plus u 1 rho 1 minus rho 0 by delta x. Okay, let us say this is the first term, the second term will be rho 2 u 2 minus u 1 by delta x, okay, and plus u 2, okay, rho 2 minus rho 1 by delta x, right, and you can see that their terms are not getting cancelled out, because here rho 1 is multiplying to u 1, here rho 2 is multiplying to u 1, right, and similarly there are other differences also, right. So, this property that when you integrate it boundary to boundary, only the boundary terms should remain, it is called the conservation, and the conservative form basically shows a telescopic collapse. That means, all the internal terms, whatever error you might be accumulating because of the discretization, because of the approximation that you have, this is the approximation, are getting cancelled out, and finally, you are getting the effect of the boundaries, which is what you should get if you are using a conservative form. If you are not using that, you will get this non-conservative form, which is you will not see this property. So, that is why when we talk about compressible flow, we tend to use this conservative form, okay, mostly. Okay, so, this was for the momentum equation. In next class, we will go through the energy equation, and then we will also discuss about the Navier-Stokes equation, what happens when you have the viscosity kicking in. Okay, what are the new terms which appear in the equation that we have seen till now. Okay, the momentum, the mass equation, as we told, they will not change. Momentum equation, because of the viscous forces, we will have some more effects that we will see in the next class. Okay, thank you very much.